and all there. Thank you very much for coming here. It's a real pleasure to have Axel Kleidon here today and give you a bit of a background of him. He got his Ph.D. in 1998 at the University of Hamburg, and then had a postdoc at Stanford, and then joined the faculty in Maryland in 2001. And then from 2006, he is now group leader at the MPI on biogeochemistry in Jena. And he's also, maybe not everybody will know that he's one of the chief editors of Systems Dynamics. Yeah. That's a journal we publish a lot in, so it's really, for the system science community, really a fantastic journal. Axel.
Yeah, well, thank you. Yeah, thank you also for inviting me on my way back. So, yeah, I want to talk about thermodynamics today, or actually about entropy. And usually, I mean, my perception is that usually people are always a little bit intimidated first, and I think it's, the way it's treated, it can get very quickly very complicated with, partial differentials and so on. And on the other hand, I think it has some really, it has something really basic to it. It feels like it's something really important. And so I want to, I hope I can show you that it's actually really central to driving the dynamics of the Earth system. And so, so that it doesn't stay just abstract, I actually want to apply it also to the hydrological cycle, where we have worked on, where one can, where I hope I can show you that you can really get predictions or estimates. Let's call it estimates. It was not about the digits, but it's sort of about the magnitudes that you can get from this approach. And yeah, so my point is, in the end, what entropy does is it actually constrains how much work can be done in Earth systems. And work is really central to do interesting things, like move things around or lift things, or chemically transform things. And what I also want to show here, sort of in the latter part of the talk, is that it also affects the way of how your variables, the kind of distributions you would expect. And it's still sort of work in progress, the last part, but I'm quite excited about it. And together with an Italian colleague, Antonella, and her group in Firenze. And I think it again makes it clearer how thermodynamics, or how the dynamics that are underlying our system processes in the end reflect something like disequilibrium and so on. And well, to introduce entropy, my favorite example is actually something from everyday, every morning, or even here I had my hot cup of coffee, and when it comes to sort of basic rules of physics, well, we all know energy conservation, so no energy gets lost or is created. But that's not enough. Yeah. So if we have a hot cup of coffee in a room and wait, then eventually it gets cold. It doesn't mean that the energy went away. It just means that the room got slightly warmer. So you basically level out this temperature difference. And so energy is conserved. And what actually happens is that, by redistributing the heat in the room, you actually increase the entropy of the system. Yeah, and so in that sense, entropy has also been called the error of time. It really tells you in which direction things go. But there's something more to it too, because when you have hot coffee, and like in the morning on the kitchen table, there's a nice smell in the room, right? You can smell the coffee. And why can you smell the hot coffee? Well, it's because you have air rising above the coffee. You have like little plumes coming up, and it takes the smell of the coffee inside spreads it around the kitchen, and so you can smell it. That doesn't happen with cold coffee. Those are the cup of coffees that you probably forget in your office, and you forgot that there was still coffee left in there. Yeah. So, and that tells us something about dynamics, because it means that when you have a hot cup of coffee, you can perform work, you can set air into motion, You can spread this line. And this work is driven by the temperature difference. And this is basically where entropy comes in. It's a form of disequilibrium. The difference in temperatures is a difference, it represents disequilibrium, and that can be used to perform work.
Sorry, I think that's the you dropped it from Zoom, so there's no.
Okay. So what should I do?
Probably rejoin the Zoom because it's not a shared screen anymore.
It's not a screen. Okay. No.
Sorry.
Okay. That's strange. I thought I shared it.
Yeah, at the beginning was the good, but I just saw it's still not there anymore.
No, right. Yeah. So.
Oh, yes, no, it's good. Yeah, thank you.
Okay, so now you can see the cup of coffee also virtually. It's a virtual cup of coffee anyway. Okay, yeah, so it's the temperature difference that is really relevant. And in the end, what it comes down to is that entropy, or this difference in entropy, is what limits the ability to perform work. And now, well, what does that mean for the Earth system? And for the Earth system, it comes down to the question, how can you actually generate work out of sunlight? Yeah, and well, so when you look at the Earth system, actually the main difference thermodynamically between the radiation that we receive and the radiation that is emitted from the Earth is the characteristic temperature that is associated with it. So solar radiation, was emitted by the sun with a temperature of 5,500 degrees centigrade, or somewhere there. And as it is being emitted, so you have a hot something, and it emits radiation. It's locally in what's called thermodynamic equilibrium, the emission of radiation of visible light, or sort of, the solar spectrum is more or less in thermodynamic equilibrium with the hot sun. And then as the solar radiation goes through space on the way to the Earth, nothing happens. So in other words, the composition of the radiation stays the same, and so does the entropy of the radiation. And then when it, it reaches the Earth's orbit, then you are far away from the sun. When you absorb and re-emit this radiation, then you emit it at a much, much colder temperature, known as the radiative temperature of the Earth, which is like minus 18 degrees centigrade. Yeah. And so embedded in these two forms of radiation, solar radiation, most sort of centered around visible light, and terrestrial radiation, what the main difference is that they have different entropies. Yeah, and they don't have, it's not sort of the usual classical thermodynamical thermal entropy, but it is a radiative entropy. And when you want to understand what it actually means, well, it means that, when you go to the quantum physical, the perspective of, where does the energy, or how is it actually being transported, when you go to the scale of atoms and electrons, then radiation is basically a flux of photons. And what it means is that that terrestrial radiation, the radiation and the infrared the Earth emits, those are many more photons leaving the Earth than the photons that the Earth absorbs. Yeah, and the energy amount is the same, or the rate of heating and cooling is the same, it's a balance. But it's basically the number of photons that is substantially increased by absorption and re-emission. So now you can basically think about, okay, so what happens during this step? So, okay, so you get, energy in, you get energy out, but, you have sort of this, if you want, like this hot coffee getting cold, right? I mean, so what happens to the radiation? Well, when solar radiation is absorbed at the Earth's surface, then what happens is what's called thermalization. Thermalization is a process where solar radiation turns into heat, and it turns into heat at a much colder temperature, which is, basically the surface temperature of the Earth. And so, basically it means that, you have some excitement, and then, those excited states, they sort of decay back to the ground states and so on. So all this low entropy from solar radiation is being basically not used and just produces a lot of entropy. So the entropy here is already a lot higher. And then as you emit radiation from the surface, and then it gets reabsorbed in the colder atmosphere and re-emitted into space, then again, you actually degrade the energy further to higher entropy. So radiative transfer is another way of how this is basically degraded. Or when I put down here that this is basically these are two processes here that actually don't perform work. It's they produce entropy, but you don't perform work. Now, the interesting processes are the ones that do perform work. And so, for example, we have heat engines. Yeah, I mean, this is sort of like a power plant, where you have a difference in heating and cooling at different temperatures. You heat the surface, atmosphere cools, so you have a temperature difference and some heat fluxes from the surface into the atmosphere. And from that, you can derive work, you can generate motion, and this motion eventually gets back into heat because you have friction at the surface, and so it results in some kind of steady state. And so on this right side here, I'm going to draw processes that actually perform work. These processes basically, you could call it, they drive dissipative systems, because then in the end, it's being dissipated. Some of the, so if the atmosphere performs work, some of that work also goes further into the ocean, like we talked about earlier, generating waves, and then the wind-driven circulation and so on. And so you have, actually, you can have cascades of, you have initial work being performed, and then, you have cascades where the atmosphere performs work on something else, and then something else performs even further work. I mean, the hydrological cycle is included in here too, and once you have water being lifted and it rains down, then you have some dissipation of the raindrops. Once the raindrops are on land, then they flow into rivers, they can perform work in transporting sediments and so on. So I think, to me, this is already I mean, I've tried to figure out what entropy is good for I don't know, maybe 20 years or so, and I think this is basically what it is, that you think about Earth system processes in terms of whether they perform work or whether they don't perform work. Yeah. Anyway, okay, but there are also two other processes where how you can derive work from sunlight. The one is photosynthesis. And photosynthesis is different because it doesn't involve heat. Yeah. So what photosynthesis does in the first step is, so it uses light, it uses the short wavelengths, the energy-rich photons, to perform, well, it breaks up water, and then it performs charge separation. So you have H plus and electrons, and then Stefan probably knows more about photosynthesis with NHDP, and I don't know what the different steps are, that until it somehow gets generates chemical, as a result of work, you get chemical free energy in form of carbohydrates and oxygen, and this energy is then dissipated by the biosphere in terms of metabolisms. Yeah, I mean, also us, not now. I mean, I don't see anyone eating, but when we consume carbohydrates, in the end we turn them into heat, and this heat we release to the environment at a certain temperature, and then produce entropy, increase the entropy of the system. And well, I still have one a little bit of space left here at the top, and there another way to do it, to derive work from solar radiation is actually by photovoltaics. And photovoltaics, well, seems like that's not really a natural thing, but it's, you know, human derived technology. But on the other hand, you know, we are part of the whole system as well. And to me, I mean, our photosynthesis, or photovoltaics actually does something similar to photosynthesis. It performs work of charge separation, but then that's it, right? I mean, you just put a wire to it and you export this energy in terms of a grid. And so photovoltaics is actually substantially more efficient in generating work from sunlight than photosynthesis is. I mean, it's like a factor of 20 or something. But I mean, okay, so that's you know, trying to sort of summarize the, if you want, the thermodynamics of the Earth system in, you know, like one slide. You know, so we have these processes that don't perform work, they just produce entropy. We have processes that perform work and then drive dissipative systems, and you know, be it climate or biosphere or, you know, human societies, if you want. Yes, and then what I want to show you actually in the application to the hydrologic cycle is that, you know, once work is being performed, and especially the physical, you know, the heat engines, they perform work, and then the motion that is being generated actually sets further constraints, that sets indirect constraints. And so the one it's like a transport constraint, and the one example I want to show is the application to the hydrological cycle. So
Can I ask a quick question?
Yeah, sure.
Because in the beginning you mentioned that the amount of energy coming from the sun is equal to the amount of energy that it's radiated, but that's not true, right? That cannot be true, because the temperature is much lower, you said. So the energy that's coming off is much less, but that's why you dissipate. Right?
Well, the balance is, I mean, there's a slight imbalance in the energy balance because of global warming, actually, but otherwise.
No, but I mean, if you have a spectrum at minus 18 degrees Kelvin, there's much less heat, then much less energy than in 5,500 Kelvin.
Yes, that's good.
So the energy is much less.
No, hang on. Yeah, I mean, that's a very good point. I mean, I think good point to clarify that here. Yeah, so the thing is that we're actually not balancing here the radiative flux like the sigma T to the 4 of solar radiation with the sigma T to the 4 of the Earth. What actually happens and what generates the disequilibrium between solar radiation and terrestrial radiation is that when we are at the Earth's orbit and we are 150 million kilometers away from the sun, then the solar radiation is out of equilibrium because you have energy being spread over a much larger sphere that would encapsulate the sun. And so how this is basically manifested itself is that, you know, when you don't have a cloudy day, but a sunny day, you know, your sun is only a very small solid angle of your sky, but the emission to space is actually over the whole solid angle. Yeah, and so the sigma T to the 4 of the sun with a 5,500 degrees centigrade enters the Earth only through the very narrow solid angle that the sun covers in the sky. And this radiation goes over the whole 4 pi of the solid angle. Does that make sense?
Yeah. Yes, it's the energy density, and then you have to multiply with appropriate volume. So that's what you're saying.
Yeah. Right. So the fluxes are balanced because otherwise we would get an increase in temperature. And when this is why they are not completely balanced, is because we do see an accumulation of heat in the ocean, for instance, as a result of global warming.
Okay, thank you.
Yeah, sure. Yeah, okay. Yeah, so now I want to give the example for the hydrological cycle and to think of the hydrological cycle as a thermodynamic system. And the way I would like to start it is sort of to say, okay, so when you think of it in terms of a thermodynamic system, it's always good to think of where's the reference point. And the reference point is equilibrium. And for water vapor, the equilibrium point is basically saturated air. So like this, gray November day, sort of similar as outside, whatever, yeah. And so when you then want to think of the hydrological cycle as a disequilibrium system that is maintained in disequilibrium, it's more like, hang on, I missed that part. So in equilibrium, what you actually have is that the fluxes of evaporation and condensation, they're locally balanced. Yeah, and doesn't mean that they're necessarily zero, but the net flux is zero. And so, locally you have the same flux. So when you deal with disequilibrium and unsaturated air, this is here, summer day, somewhere in southern Denmark, you have, it's like, you separate your evaporation and your precipitation spatially and temporally. So you evaporate at the warmer surface, you condense in the colder atmosphere, and thereby you can, you already have a disequilibrium. And at the same time, you have that, because you're heating the surface, you also generate motion that actually brings in the water vapor into the atmosphere. Or in terms of when you think of, when it rains, then you have condensation, heating, driving another heat engine. And so you have also motion being generated when things condense. And so you can split up this hydrological cycle or the disequilibrium into one, like two phases, one where you evaporate and one where you condense and precipitate. And then one can think, okay, so how, it's still, sort of like pretty colorful pictures, but, how can we actually use that to sort of make this more quantitative? And I think I'll stop. Go here, thermodynamics of evaporation. So I want to go into that part. Yeah, okay. So you, when we talk about the first part of evaporating, then, well, evaporation takes place when the surface is heated. I mean, the evaporation of water requires a lot of energy. So you have an energy balance that constrains how much energy input we get, like from the sun during the day. So you have heating of the surface. Heating also means that we have buoyancy. So it's warmer than the air. So you get air being accelerated upward. So you have power. So you have motion generated. And this motion sort of takes the water vapor along. But then as you generate motion, what actually happens is that you start to have two feedbacks. One is that as soon as you start more, updrafts and you actually generate more motion, you also actually enhance your heat flux. And when you have a greater heat flux, you can generate more power. On the other hand, the more you transport heat away from the surface, the cooler the surface is going to become. And I noticed I didn't put that slide in, but the power you can generate in the limit, you have an expression that's called the Carnot limit. It's basically a heat flux times the temperature difference. So the first part means that when you have more motion, more heat flux, more power. But on the other hand, when you have more heat flux, less temperature difference, that means that your second term in your power is sort of decreased. And because of that, you actually have a maximum in the power you can derive. This is something that one can calculate. One can even do it on a blackboard. But my Sarosh, Ph.D. student in my group, former, he did this sort of more numerically. But anyway, so you have this power, the maximum power, and so what we did is, we had their data sets on radiative fluxes from satellites. So, we know how much solar radiation is being absorbed at the surface. We know how much radiation comes from the atmosphere to the surface, downwelling long-wave radiation. Then we maximize power and can derive these optimum heat fluxes and temperatures from this assumption of maximizing power. And, here's the comparison to the satellite inferred heat flux and also to the satellite inferred temperatures. And, you can see that it actually correlates really well. And so in terms of estimating magnitudes, that's sort of setting the limit. And so when you think about the different ways of, how you can derive work from sunlight, it looks like the atmosphere tries to work as hard as it can. Yeah. Then, okay, so that's the starting point, but now what about evaporation? Well, evaporation is part of the heat flux. It's composed of the sensible and latent heat flux. And there too, thermodynamics can actually help. And that brings us to a concept that's called equilibrium partitioning. And I don't know how many of you have sort of like a land background. I mean, equilibrium partitioning is something that is quite common in hydrology when you want to estimate evaporation. More important is that I think what actually happens. So if you heat the surface and then you want to bring heat into the atmosphere, the most you can evaporate is if you keep the air right in contact with the surface in saturation. Yeah, so you heat the air, so you have a delta T, and you add moisture to keep it saturated. And from that, you can derive basically a fraction of how much of that goes into heating the air and how much of that goes into moistening the air. And that's sort of these cryptic fractions that I put down here. So the gamma is what's called the psychrometric constant, depends on heat capacity of the air and on pressure, I think. And the S is the slope of the saturation vapor pressure curve, which is basically Clausius Clapeyron. And so you have this partitioning into sensible and latent heat. So, I translated that here from the in terms of, in hydrology, it is called potential evaporation. So that means this is how much water could evaporate if there is enough water available. Then we can say, oh yeah, well, but in the Sahara, it doesn't rain. So what we can do is we take potential evaporation and precipitation and take the minimum. It gives you some sort of a measure for water availability. And then we can get what's called actual evaporation on land. And again, we can compare this to observations, and the comparison shows that it actually works pretty well compared to a product that's based on site measurements. We also looked at this in rainforest ecosystem using measurement towers, where our institute is also involved. This is in southeastern Brazil and Tanguro. So what's shown here is sort of the mean monthly diurnal cycle of energy fluxes. Here the June is the dry season and January is the wet season. The symbols are measurements and the lines are, it's what is predicted by maximum power. And you see sort of that this rainforest sort of appears to actually operate at this equilibrium partitioning, and both fluxes, the sensible and latent heat fluxes, sort of match really well with the observations. Yeah, and so, and I actually started or during my PhD, I worked on vegetation and on how important vegetation is, and this picture would almost seem like, or these results would seem like, that actually it's all thermodynamics, do away with the rainforest, it's all physics. And I think this is actually not right, the interpretation, because I think what it actually means is that, there is a thermodynamic limit on how much water you can evaporate. And what the rainforest does is it evolves to a point where it can actually reach that limit. Yeah, and so it's not because the system is simple, but probably the opposite. It's so complex that it actually operates at this thermodynamic limit. And So for example, the dry season, it's pretty dry, and for that you need to have enough access to soil moisture, so you need to actually have a deep reaching root system so that you can take the water and evaporate. So it's not so trivial to reach this limit. Okay. Now I want to sort of talk a little bit more about recent work we've done on precipitation. So, you know, I talked, yeah, sure, yeah,
So this maximum power principle is but that's not a thermodynamic principle. Then somehow it is an observation that you made, but it's not an explanation why this happens or something.
No, that's true. Yeah, and I mean, I think this is sort of, I would say this is still something that one can, you know, difficult to put it down or pin it down what it actually is. Yeah, I mean, so, you know, when a system performs maximum power, then it also dissipates maximally. And when it dissipates, it produces entropy. So you can call it, you know, maximizes entropy production. This is sort of a hypothesis that I was also involved in like 10, 15 years ago. But then, you know, not every process that produces entropy maximizes it. Yeah, actually the contrary is the case. Yeah, I mean, so if you maximize power by convective motion, you actually minimize the entropy production by radiation. Yeah, so, and you know, I think it's a good question. I mean, I don't know what the ultimate how you can put this into something like a principle, right? Yeah, I think that's still open, yeah, but it works, you know, and yeah, and I mean, what I like about it is that one can actually really do like you know, like climate science on the back of an envelope, you know, and get an estimate, yeah, yeah.
So continuing on the vegetation point of view, so I was wondering, so now you have an example where this whole system perfectly works. Are there also examples where it does not work? And for that, is that maybe different vegetation types, these kind of things?
Well, you know, I mean, yes, I mean, there are quite a few examples, you know, where it didn't work at first. At first it didn't work, or, you know, there was like a constant, quite a bias. And then, you know, we thought, and it took a few years, and then we thought, you know. So for example, for the diurnal cycle, you can't just use the good old Carnot limit of a heat engine, but you need to consider that the atmosphere heats up during the day. Mm-hmm. And because it heats up during the day, you have a change of entropy in your system, and you need to derive a different limit. It's similar to a Carnot limit. It's also first and second law. And you know, we call it the Carnot limit of a cold heat engine, because you basically need to heat up the atmosphere as well. And that's like an entropy term. And then you can again maximize the power. Yeah. Another example actually was the one that I showed earlier in terms of sort of you know, a large scale application of this maximum power from Sarash's work, where we noticed that in the subtropics, for example, you need to also consider the fact that in the subtropics you have heat being transported from the tropics into the subtropics, you know, well-known phenomenon. What it does to the heat engine is that you heat the engine from above, which means you can't produce as much power because you're heating it from the wrong side, if you want. Yeah, and that shifts the maximization, and that's sort of included in there. But you can show that this is actually also an effect that can reduce the deviations. Yeah, yeah. And so I'm sure there are other deviations too that one can probably identify where one can find good explanations for. Yeah.
I think you need also to have optimum conditions in other ways, like nutrients and light. You can only consume energy to the max, but there's also no shortage in nutrients or no shortage in light.
Absolutely. You know, and I think, yeah, I mean, you know, and maybe I can sort of put this to the discussion because, I mean, I think the nutrients, yeah, I mean, you can predict a lot of the biosphere without being ignorant to nutrients, you know, and means that there are some mechanisms that make sure that, that they're not limiting, But I want to sort of continue with precipitation. So that's relatively recent work we started, and so that's not driven by solar heating the surface, but it's driven by condensational heating. So in other words, it's in principle the same thing. You know, you heat by condensation, then you generate power to accelerate, and the other work that's involved is dehumidification. You remove moisture from the atmosphere. But in terms of feedbacks, they're a little different because, I mean, the first, you know, when you have more motion, you bring in more moisture, you can condense more, but you don't deplete the temperature difference. Yeah, because your heat source is not fixed incoming solar radiation, but it is how much moisture you bring in. And that leads to quite some different dynamics. Yeah, because we will see that in a minute. And then ultimately it's sort of constrained because, you know, the more you condense and the more you dehumidify, eventually, you know, you deplete your energy source in terms of water vapor. So there's also a maximum. Maybe I noticed the time is moving on, and I want to sort of show a little bit on the distributions as well. Maybe just one sort of, again, work in progress. So we, the maximum, you can express it in terms of, you know, how much dehumidification would you expect when the dehumidification event performs maximum work. And Sarosh looked at sort of like 90% extreme rainfall events across the globe. And well, it's not a perfect correlation, but it's sort of capturing the trend and the magnitude of the rainfall events across the globe. You mean this is your data set based on observations, and this is what's estimated. You know, you see some deviation, but again, you know, it's sort of like our first step in that direction, and I think it's looks quite promising. And what I like about this approach is that I think it really helps to communicate how climate works in a quite simple physical sense. So when we think about the tropical circulation, the Hadley cell, well, it's a gigantic heat engine sitting that is fueled by moisture. And to just give you the proportion, the sensible heat flux global average is about 20 watts per square meter. When you think of a tropical rainfall rate of, say, 8 millimeters a day on average, that corresponds to 240 watts per square meter. Yeah? So there's a lot of heat being released. And so we can easily imagine how, you know, this drives this tropical circulation, where you have an excess of precipitation here, and you have a deficit of precipitation in the subtropics. So also a spatial disequilibrium in terms of the hydrological cycle. One can then actually also, you know, just to illustrate that one can also apply this to like climate change scenarios, or sort of to imagine what happens with global warming. Global warming means the atmosphere can hold more moisture. More moisture means you get more powerful heat engines, right? I mean, the heat engine becomes more powerful because there's more moisture there. And so you would expect this to strengthen. And this is actually quite well known in climatology or climate science as, you know, the wet gets wetter and the dry gets drier hypothesis. And I think that one can sort of see this directly from this when viewing moist convection as a heat engine and the tropical circulation being basically shaped by this heat engine. And I think it also shows the very close relationship between sort of this, like a, you know, a cycle, a biogeochemical cycle, water cycle, and motion, and how intimately the two are connected. Yeah, so the last part I want to, and I notice I should probably.
Well, take your time. We don't have to go to protest in the center now.
Okay, maybe I can have a say that I can say something.
No work. Wait, thank you.
Yeah, so the last part is actually on the linking thermodynamics to characteristic distributions, and this is something that, you know, what I'm showing here is actually the Apennine. It's close to where the source of the Arno River is in central Italy. And that, I show this because, I mean, this was really stimulated or initiated by Antonella from the University of Firenze, who wrote an email to me to say, there must be a connection. What is it? And to sort of illustrate this sort of, when you look at temperatures, they are quite close to a Gaussian distribution. Just as an example, when you look at cloud area versus parameter relationship, you get a power law relationship. So it seems like, in nature, there are two dominant kinds of distributions. One is a power law, one is a normal distribution. So why is this? And how is it connected to thermodynamics, to the thermodynamics of the system? And well, after some years of circulating between the two of us, we sort of can think of a relationship between the two, and it's based on an interpretation of power laws that is based on a Belgian mathematician and economist Gabay, who showed that you can get power law distributions when you have entities that basically grow proportionate. I mean, he calls it stochastic proportionate growth. It means that systems grow in terms of their size. It's an exponential growth, but there's some variation in the growth. He looked at film sizes, but you can also see it for trees. There are power laws with trees or clouds and so on. And so essentially, this concerns systems that grow exponential. And when you then take sort of the aggregation of these different entities and then how they grow, then you can essentially find a power law. And I like that interpretation because I can sort of imagine what it means and relate to it. And so that results in a power law. Now, the question is, so how does that relate to thermodynamics? And I think the way it relates to thermodynamics is that when you think of Earth systems, there you can only have growth processes if you have some form of disequilibrium. And so, in other words, when we think of, we have literally a disequilibrium and then clouds, so when you deplete this disequilibrium and, you have some exponential growth, then you would expect a power law. And then when things reach an equilibrium state, then, we would be more expecting some kind of normal distribution, because there, when you perturb a system that is near equilibrium, and you perturb it, then basically it will always go back to the equilibrium state, so that it's sort of reacting symmetrically to perturbations. At the time, we applied it actually to river chemistry of the Arno River. And here, the disequilibrium is basically the rainwater at the spring of the river, and then over the course of the river, it accumulates weathered elements, and some of these weather faster, some of them weather slower, and so that's the example we used. But in principle, you can also apply to the hydrological cycle that I showed earlier, right? I mean, which is sort of driven by, you have like a dehumidification phase, and then again, sort of a system that sort of flip-flops or sort of oscillates between those states. Yeah. So for when you think about the hydrological cycle, so I talked so initially when you have equilibrium and you have precipitation, then you have work done to dehumidify. Initially exponential growth, and so you could expect with things associated with precipitation clouds having some kind of power law kind of distributions, while when you have the evaporation phase, that's sort of almost boring because it's just driven by the energy input, and you have a relatively simple linear decline there. And so with with precipitation, you have this positive feedback on growth that you would need to sort of follow the reasoning by Gabay. So, when you have condensation, you have more heating. More heating means more power means more motion brings in more moisture, so you have more condensation, and so you would have a positive feedback that is ultimately slowed down because you're also dehumidifying. And in the end, reducing the water vapor, your fuel for that process. So maybe one can write that similar to sort of this logistic equation. I think it's sort of an equation for population biology, but I think you probably can also apply it to purely physical systems. Yeah, and so Sarosh, he's quite, always very motivated, and so he said, okay, he looks at distributions, so when you look at tropical evaporation rates, they sort of look more like a normal distribution, while with precipitation you find this more like a power law kind of distribution that is quite different. Yeah, and so now I'm actually coming to the end. So I hope I I started off with entropy and the hot cup of coffee and how entropy constraints work, and that it's this equilibrium that you need to generate work, and also showed how you can or how apparently the atmosphere figured out how to maximize the power it can derive from sunlight. Applied to the hydrological cycle, then I talked about evaporation being sort of the combination of this maximum power combined with this energy balance constraint, or this partitioning, this equilibrium partitioning that results in evaporation patterns that one can actually predict quite well. With precipitation, it is maximum work to accelerate and dehumidify, and then it would seem that this viewing the system in terms of disequilibrium and power, and whether you have these positive feedbacks on the dynamics, that this can actually help us to understand why you have sometimes normal distributions and sometimes power law distributions. Yeah, and so I hope that at least I sort of planted a seed to think of that entropy is actually quite a useful concept in, say, Earth system dynamics. Yeah, thank you.
Very much, really nice. Well, there was already some discussion. More. So who? Yeah.
Well, one slight remark when you spoke about photovoltaics and photosynthesis, it might also be nice to mention photoredox processes as a special kind of redox processes induced by solar light. But more on the evaporation precipitation cycle, I'm wondering where pressure is in. Where do you put it as a transport mechanism?
Pressure.
Yeah, because with high pressure, low pressure, that's of course the movement of air.
Well,
and somewhere in between.
Yeah, it's somewhere in between. Yeah. And in principle, there's maximum power in the vertical. You can also flip it, 90 degrees, and then you can also figure out how much heat is being transported from the tropics to the pole. Yeah, and it's something that say commonly is expressed in terms of pressure differences. And then one can ask, where does the pressure difference come from? And it's usually, it's related to heating differences. Yeah. And so I would say the pressure differences are sort of an intermediate step. And in the end, what's driving are the radiative fluxes. Yeah, because they are the ones actually in the end which add or remove entropy. And so whatever happens in between is sort of constrained. And you can relate it to pressure differences. And although, the connection to, in meteorology, you call it available potential energy. That's sort of an intermediate step from radiative or from differences in radiative heating. You get available potential energy, and that you can convert into kinetic energy. And that's something that we haven't quite figured out. I mean, it's a bit of a hand wavy way we sort of linked it, but it could be related because, I mean, basically what happens is that when you have hot or warmer tropics, colder pole, then your density or your pressure difference with height, your pressure decline with height is more rapid when the air is more dense or colder. And so in the cold region, you have a more rapid pressure decline than in the tropics. And so you start developing a pressure difference that can cause the onset of motion. So, I think what it means is that this heat engine concept for driving atmospheric dynamics is not inconsistent with pressure differences and so on. It's just a wider frame of the system description.
Yeah.
And it seems like it makes it simpler.
Okay, yeah, it must be part of the work.
Yeah.
But I was wondering how is it indeed interrelated as part of the work?
Yeah, I mean, I think it's completely related. Yeah, I mean, so you have it's when you go to the details, it always gets more complicated, right? Because then then you also have like that you get a pressure difference a lot, but then you get a you just relocate mass, and then you have differences in pressure at the surface, and so you have a backflow and so on. So that gets more complex. But mainly, when you think back in terms of the horizontal, I mean, I think what I find fascinating is that, and also like boundary layer dynamics, convective boundary layer, can get really complicated with turbulent cascade and so on. You have like big rolls, smaller rolls, and so on. But to me, it seems like that these thermodynamic constraints are in the end it's limiting the system, no matter what it does. Yeah, but it sticks in these limits and or in this constraint set by thermodynamics, and it is that in the end that makes it relatively simple and predictable. Yeah. Does it make sense?
Yeah, I think the line is also continuing. Because earlier you also mentioned the role of friction, and when it comes to movement of air masses, friction also plays a role. So in the end you have to combine it all together and then see what the couplings are. But it's quite complex, I think, to find it out.
Well, I mean, in the end, I mean, all the power that is being generated, of course, gets dissipated, right? And so by friction.
Yeah.
So in that sense, I mean, it didn't explicitly mention it, but I think what it means is that also the frictional dissipation is limited by how much work the system can do, right? And the work apparently is is being maximized, and that is being limited by thermodynamics. So it's like a sequence.
Oh, sure. There's also with rivers, they have the Manning coefficient to deal with the friction on the riverbed, etc. Something similar will be valid for air with land surfaces. But then you also lose energy in that way.
Oh yeah. I mean, absolutely. I mean, friction is part of the.
Transformed. In better ways.
Yeah.
Any other question? Yeah.
Oh.
No, go ahead.
Yeah, I really like this sort of perspective because I normally work on photosynthesis and transpiration, but they're very much from the leaf level, so it's like basically a much different scaling mechanism. I have one question about one of the early slides that you showed, the partitioning of the energy between the entropy of all the dynamics in the hydrological cycle and then the photosynthesis and the photovoltaics. Would you mind putting it up? Because
sure.
I kind of
I think it was quite at the beginning.
yeah.
This one here, right?
Yeah. And I was wondering, I'm not sure if it is relevant for the way you calculate things, but I was just thinking about like what plants are doing at leaf level. Actually, the chemical energy storage into sugars and all that is to some extent connected to the evaporation that is happening at the leaf level.
Yeah, yeah.
Some of the energy is then actually what is not used for the chemical stuff is then being used for evaporation because the photosynthesis and transpiration are coupled at the leaf. And it's not so much, it's like 1 to 10% or so. So I was wondering, does it influence, so because it creates a little feedback there between the chemical energy and then the availability of energy for.
Well, I think that photosynthesis uses some of the, of course, some of the energy and sort of takes it out. But then at the same time, it also respires, right? I mean, the plant organisms respire, and so they release heat. And I think, I don't know, it didn't seem to make much of a difference. I mean, maybe it's in our uncertainty or so, but we didn't consider that that energy that photosynthesis uses. Yeah, so we estimate evaporation rates, and then even without recognizing that plants do the evaporation.
Yeah.
And actually, maybe it's a little detour, but I think what's fascinating is, how do you get actually from the leaf to the area, right? Because what I show is basically a view that's only dealing with square meters. And on the other hand, there's the leaf scale.
Yes.
Yeah, I think that's certainly a complex question of how you actually translate scale behavior to square meter.
Yes, and it's not trivial. There's a
If
you just multiply with leaf area index, you get completely different results.
Yeah.
Yeah, but I can imagine the energy in photosynthesis is at slightly longer time scales dissipated through respiration. In the end, it cancels out. Yeah. Okay.
Yeah.
Cool. Thanks.
Okay. Yeah. Oh yeah, thanks. It was a very nice presentation. So in one of the last slides, maybe not the last, but the previous one.
Yeah.
So there was this hypothesis that I found could be a bit restrictive on the cycle in which you start from the power law and then it turns into a Gaussian.
Yeah.
And then in the next slide, you showed some fittings to a Gaussian.
This one.
Yeah, this one, which are, I wouldn't say that that's actually that Gaussian because it still has certain heavy tail, certain fingerprint from the heavy tail. So isn't it too restrictive just to assume that it goes straight to a Gaussian, because there are in fact many distributions that emerge out of entropy maximization, like the exponential family of the distribution, like gamma distributions, Weibull distributions, and then also these distributions still preserve certain power tails. So, and that allows to go out from that distribution to capture a cycle, in fact.
Yeah. I think that's a good point. I think what I find more I think in terms of evaporation, I don't think that there is a really long tail in the distribution, simply because for evaporation you need energy, and so it's quite a constrained process. With precipitation, I think it is something quite different, because once you have this, the energy is basically your water vapor that you can condense, and how much energy you have accessible to condense depends on the scale over which you can draw it in. Yeah, and so the more motion you generate, the further the motion reaches, the more you can harvest, if you want, the water vapor. And there I can imagine heavy tail. And I think that sort of relates to this diagram here in a way too, because when you think of exponential growth being sort of at least in some systems being sort of the central piece of power law distributions, then they can't grow indefinitely. But it's sort of set by the disequilibrium that you have in the system, and that sort of restricts how far you would expect such dynamics, how far you would expect power law scaling to actually go, and when it would actually start to stop because you don't have a disequilibrium anymore to deplete. Does that make? And I actually also thought about the Weigel distribution, for instance, because it's associated with wind.
And especially that one because the power law has this scale-free feature, but the Weibull distribution doesn't have it and still is a heavy tail distribution. So yeah, that could be something.
Yeah.
to eat.
Yeah, I think there's certainly, yes, there are more than.
Yeah, because when you have a power law, I mean the process can diverge because of this scale free. But with the Weibull, it doesn't diverge.
Yeah.
So when you sample out of the Weibull, you can actually have a process in which numbers do not diverge.
Yeah. I mean, I think it's more or less the same what we're saying. I mean, I think it doesn't contradict.
No. I mean, it's just that I find very restrictive just to bring it until the
Power law.
Gaussian.
Yeah. Well, I've been thinking about the Weibull distribution, but I mean, just sort of on the side because also like with wind energy, and I think quite and the Weibull distribution is sort of a little sort of a strange distribution because when you look at the wind speed components individually, they can be quite Gaussian, right? And so it's of course then when you look at when you take wind speed as the magnitude, then you get this sort of unusual distribution away because you basically square two Gaussians and take the root out of it. Yeah. So yeah, I don't know. Just some thought on it.
Okay, and last question. Yeah.
Of course, yeah. Well, really fascinating. Yeah? So maybe about the wet scan and weather and the dry scan and weather. Yeah? So from your perspective, from your thermodynamic perspective, and what we try to understand is, let's say, how can we increase the scale, so the convective available potential energy here for dry areas, and is it then that, from your perspective, is it then if we can decrease, let's say, the tropical, if you deforest tropics, would that mean that you can get more energy for the drier parts?
When you deforest the
If we deforest the tropics, meaning that your Hadley cell become less important, let's say, does it mean then that the dry areas, so the Mediterranean, etc., will become potentially
where you can have convective rainfall?
So would that mean, in your way of thinking?
Well, I mean, I think
to make the whole climate in thermodynamics in your way, etc. So can you play one with that, and should that be in?
Well, I mean, I think one could, in principle, evaluate this, right? I mean, the thing is, the power that you get from the convective event must be greater than the inhibition due to sinking air. Basically, you need to perform work against that.
Yeah.
And if that's larger than what you need to overcome the subsidence, then I guess that would be and reach condensation.
And which, of course, it's not a deal with the strength of getting the squeeze, of course.
Yeah. So I mean, I think that is sort of you could think along that and figure out the criteria or something. Yeah. But then, you know, if it is about getting fresh water in the subtropics, energetically, it's probably more efficient to desalinate the seawater.
From an energy perspective,
Yeah.
probably, yeah. Yeah.
Okay, well. We have a little present for you
Oh, thank
from
you.
the center.
Yeah.
And thank you very much for a
Yeah,
nice
thank
talk.
you.
Let's take